Hey guys, I'm Sarah Wang, General Partner on the A16Z Growth Team. Welcome back to our AI Revolution series. In this series, we talk to the GenAI builders who are transforming our world to understand 1, where we are, 2, where we're going, and 3, the big open questions in the field. Our guest this episode is Dmitri Dolgov, the co-CEO of Waymo. Dmitri has led Waymo to solve some of the biggest challenges in bringing AI to the real world. And after tens of millions of miles of testing, Waymo's vehicles have shown themselves to be safer and more reliable than human drivers, myself included. Dmitri has a unique perspective, given that his work has spanned multiple AI ML development cycles across decades. He was an early pioneer in self-driving cars, working with Toyota and Stanford on DARPA's Grand Challenge before joining Google's self-driving car project, which then evolved into Waymo. In this conversation from a closed-door event with A16Z general partner David George, Dmitri talks about the potential of embodied AI, the value of simulations and building training data, and his approach to leading a company focused on solving some of the world's hardest problems. Without further ado, here's Dmitri in conversation with David.
Maybe to start, take us back to Stanford, if you will, and that was when you first started working on the DARPA project, and maybe give us a little bit of your history of how you ended up from there to here.
My introduction to autonomous vehicles was when I was doing a postdoc at Stanford that you just mentioned, David. This was during, I got pretty lucky with the timing of it. This was when the DARPA Grand Challenges were happening. DARPA is the Defense Advanced Research Project Agency that started these competitions with the goal of boosting this field of autonomous vehicles. And the one that I got involved in was in 2007. That was called the DARPA Urban Challenge. So the setup there was, it's kind of like a toy version of what we've been working on since then. It was kind of supposed to mimic the driving in urban environments. So they kind of created a fake city on an abandoned airbase, and they populated it with a bunch of autonomous vehicles, a bunch of human drivers, and they had them do various tasks. So that was kind of my introduction to this whole field, and it was a bit of a, I think DARPA, these challenges are often by people in the industry considered kind of a foundational, pivotal moment for this whole field, and it was definitely that for me. It was like a light bulb, light switch moment that really got me hooked.
What was like the hardware and software that you guys had at that point? This is 2007.
Yeah, no, it was at a very high level, not unlike what we talk about today. A car that has some instrumentation, so you can tell it what to do, and you get some feedback back. Then you have kind of it's called a pose system, a bunch of inertial measurement system, accelerometers, gyroscopes that kind of tell you, and GPS tells you how you're moving through space. And it has sensors, radars, lidars, and cameras. The same stuff we still use today. And then there's a computer that gets the sensor data in and then tells the car what to do, and a bunch of software. And software had perception components and decision-making planning components and some AI. But of course, everything that we had, like each one of those things over that how long has it been? Almost 18 years, more than that. It's changed drastically, right? So when we talk about AI today versus AI we had back in 2007, 2009. Nothing in common. And similarly, everything else has changed. The sensors are not the same, computers are not the same.
Yeah, of course. So then, okay, so at that point, that was the pivotal, that was like the light bulb moment. And then at that point, you said, okay, I'm at Stanford, I want to make this my career, right? Is that, and then it was Toyota, and then where did it go from there?
I don't know if I thought about it in those terms. I was like, this is it.
Pretty cool to work on.
This is the future. I want to make it happen. I want to be building this thing. Career, okay, that can wait. But that was the next step. That was the next big step. Is a number of us from the DARPA challenge competitions started the Google self-driving project. It was about a dozen of us. Then in 2009, came together at Google with support and excitement from Larry and Sergey to see if we can take it to the next step. And that then we worked on it for a few years, and that project then became Waymo in 2016, and we've been on this path since then.
Okay, so we have this new big breakthrough in generative AI. Some would say it's new, some would say it's 70 years in the making. how do you think about layering advances that have come from generative AI to what many would describe as more traditional AI or machine learning techniques that were kind of the building blocks for self-driving technology up to that point?
Yeah, great question. So maybe I can, generative AI is kind of a broad term.
Sure.
So maybe you can, maybe take a little bit of a step back and talk about kind of the role that AI plays in autonomous vehicles and kind of how we saw the various breakthroughs in AI map to the space of our task, right? So, as I mentioned, AI has been part of self-driving or autonomous vehicles from the earliest days. Because back when we started, it was a very different kind of AI, ML, kind of classical decision trees, classical computer visions with kind of hand-engineered features, kernels and so forth. Then, one of the first really important breakthroughs that happened in AI and computer vision, but really was important for our task, was the advancement in convolutional neural networks, right around 2012. Right, many of you are probably familiar with AlexNet and the ImageNet competition. This is where AlexNet kind of blew away out of the water all other approaches. So that obviously has had very strong implications for our domain, like how you do computer vision, and not just on cameras, right? How you run, you can use convnets to interpret what's around you and do kind of object detection and classification from camera data, from LiDAR data, from your imaging radars. So that was kind of a big boost around that 2012, 2013 timeframe. And then we played with those approaches and tried to extend the use of convnets to other domains, just be a little beyond perception with some interesting but limited success. Then another big, very important breakthrough happened around 2017 when transformers came around. It had a really huge impact on language understanding, language models, machine translation, so forth. And for us, it was a really important breakthrough that really allowed us to take ML and AI to new areas well beyond perception. Right? So if you think about kind of transformers and the impact that they had on language, kind of the intuition is that they're good at kind of understanding and predicting and generating sequences of words, right? In our case, we think about in our domain, think about the tasks of understanding and predicting what people will do, like other actors in the scene, or the task of decision making and planning your own trajectories, or in simulation, kind of generating generative AI, our version of generative AI, kind of generating behaviors of how the world will evolve. These behavioral, like these sequences are not unlike sentences, right? You're kind of operating the state of objects, right? And there's kind of local continuity, but then the global context of the scene really matters. So this is where we saw some really exciting breakthroughs in behavior prediction and decision making in simulation. And then, since then we've been on this trend of models getting bigger. People started building foundational models for multitasks, and most recently, all of the the last couple of years, all the breakthroughs in large language models, modern day generative AI, visual language models where you kind of align image understanding and language understanding, and there's been most recently one thing I'm pretty excited about is kind of the intersection or combination of the two. So that's what we've been very focused on at Waymo most recently, is taking kind of the AI backbone and all of the AI, the Waymo AI that is over the years we've built up that is really proficient at this task of autonomous driving, and combining it with kind of the general world knowledge and understanding of these VLMs.
One of the things that you just mentioned is the role of simulation. And how that has been, you guys have had major breakthroughs in the use of simulation. And this idea in the recent breakthroughs in generative AI around synthetic data and its usefulness is somewhat in question. I would say in your field, this idea of synthetic data and simulation is extremely useful, and you've proven that. So maybe you could just talk about the simulation technology you guys have built, how it's allowed you to scale, build that real-world understanding, and maybe how it's changed in the last few years.
Yeah, definitely. So it is super important in our field. And largely, if you think about this question of evaluating the driver, like, is it good enough? it's how do you answer that? There's a lot of metrics and a lot of data sets you have to build up, and then how do you evaluate the latest version of your system? You can't just throw it on the physical world and then see what happens. You have to do it in simulation. But of course, the new system behaves differently from what might have happened in the world otherwise. So you have to have a realistic closed-loop simulation to give you confidence in value. So that is one of the most important needs for the simulation. You've also mentioned synthetic data. I guess that's another area where simulation allows you to have very high leverage. Right? You just got to explore the long tail of events, right? Maybe there's something interesting that you have seen in the physical world, but you want to modify that scenario, and you want to kind of turn one event into thousands or tens of thousands of variations of that scenario. How do you do that? This is where the simulation comes in. And then, lastly, if you sometimes want to evaluate and train on things that you've never seen, even our very vast experience. So this is where purely synthetic simulations come in that are not based on anything that you have seen in the physical world. So in terms of technologies that go into play, it's a lot, and that is like a huge generative AI problem. But what's really important is that simulator is realistic. Right? It has to be realistic in terms of your sensor or perception realism. Right? It has to be realistic in terms of the behaviors that you see from other dynamic actors. Right? You have, if other actors are not behaving in a realistic way, like if pedestrians are not walking the way they do in the real world, you need to be able to quantify the kind of the scenarios that you create in simulation to the realism and the rate of occurrence in the physical world, right? It's very crazy to sample something very easy to sample something totally crazy in a simulator, but then what do you do with that? So I think that brings me to the third point of realism, is that it has to be kind of realistic and quantifiable at the macro level, at the statistical level. So you can imagine there's a lot of work that goes into building the simulator that is large scale and has that level of realism across those categories. And if kind of intuitively think about it, to build a good driver, you need to have a very good simulator. But to have a good simulator, you actually have to build models of realistic pedestrians and cyclists and drivers, right? So it's you kind of do that iteratively.
Yeah, of course. And then by having this simulation software that is very good at mimicking real world and very usable in the sense that you can create variables in the scenes, you can actually give the driver multiples of the amount of experience that they have on the road.
That's exactly right.
In real miles driven. Is that right?
That's exactly right. We've driven tens of millions of miles in the physical world. At this point, we've driven more than 15 million miles in full autonomy, what we call rider-only mode. But we've driven tens of billions of miles in simulation. So you get orders of magnitude of an amplifier.
Speaking of multiples of miles driven, one of the hotly debated topics in the AI world today is this concept of scaling laws. So how do you think about scaling laws as it relates to autonomous driving? Is it miles driven? Is it certain experience had? Is it compute? What are the ways that you think about that?
So model size matters. So we are seeing scaling laws apply to a lot of typical old school models are severely undertrained. So if you have a bigger model, you have data that actually does help you. You just have more capacity, they generalize better. So we are seeing the scaling laws apply there. Data, of course, hugely matters, right? But it's not just counting the miles, right, or hours. It has to be the right kind of data that teaches the models or trains the models to be good at the rare cases that you care about. And then there is a bit of a wrinkle, because then you can build those very large models, but in our space it has to run on board the car, right? So you are somewhat compute constrained, so you have to distill it into your onboard system. But we do see trend, which is common trend, and we see that play out in our space, where you're much better off training a huge model and then distilling it into a small model than just training small models.
Yeah. I'm going to shift gears a little bit, and I'm going to do a sort of simplifying statement, which is probably going to drive you crazy. But the DARPA school of thought is there's sort of a rules-based approach, right? A more traditional kind of AI-based approach with a massive amount of volume, and you document edge cases, and then the model then learns how to react to those. The more recent approaches from some other large players and startups would say, hey, we just have AI from the start, make all the decisions end to end. You don't need to have sort of all that pattern recognition and learning, like the end-to-end driving that is kind of a tagline out there. What is your interpretation of that approach, and what elements of that approach have you taken and applied inside of Waymo?
Yeah, no, I think it's kind of, sometimes it's the way people talk about it is kind of this weird dichotomy. Is it this or that?
Yeah, of course.
But it's not. It's that and then some, right? So
right.
It is, big models. It is end-to-end models. Yeah, it is generative AI and combining, these models with VLMs, right? But the problem is it's not enough. Right. So we all know the limitations of those models, right? And that's, and we've seen, through the years, a lot of these breakthroughs in AI, right? Content nets, transformers, big end-to-end foundation models. They're huge boosts to us. And what we've been doing at Waymo through the history of our project is kind of constantly applying and pushing forward these state-of-the-art techniques ourselves in some cases, but then applying them to our domain. And what we've been learning is that they really give you a huge boost, but they're just not enough. Right. So in the kind of the theme has always been that you can take your kind of latest and greatest technology of the day, and it's fairly easy to get started. Right? Like the curves always look like that, and they've been kind of the curves have been shaping, but the really hard problems in that remaining 0.0001%,
right.
And there it's not enough. So then you have to do stuff on top of that, right? So yes, you can take nowadays you can take an end-to-end model, go from sensor to trajectories or actuation. Typically you don't build them in one stage, you build them in stages, but you can do like backprop through the whole thing. So the concept is very, very valid. You can combine it and with a VLM, and then you add closed loop simulation of some sort, and you're off to the races. You can have a great demo, like almost out of the box. You can have an ADAS or a driver assist system. But that's not enough to go all the way to full autonomy. So that's where really a lot of the hard work happens. So I guess the question is, not is it this or that, it's this, and then what else do you need to take it all the way to have the confidence in, so that you can actually remove the driver and go for full autonomy. And that's a ton of work. That's a ton of work through the entire kind of life cycle of these models and the entire system, right? So it starts with training. Like, how do you train? How do you architect these models? How do you, evaluate them? Then, if you put in a bigger system, the models themselves are not enough, so you have to do things around them. You have to, they have modern generative AI is great, but there are some issues with, hallucinations, issues with
explainability.
Exactly,
right.
Exactly. So, they have some weaknesses in kind of goal-oriented planning and policy making, and kind of understanding this, 3D space, operating in this 3D spatial world, right? So you have to add, something on top of that. We talked a little bit about the simulator. That's a really hard problem in of itself. And then, once you have something, once you deploy it and you learn how do you feed that back. So I guess this is where all of the really, really hard work happens. So it's not like end-to-end versus something else. It is end-to-end and big foundation models, and then the hard work.
And then all the hard work. Yeah, it totally makes sense. That is a great segue into all of the progress that you guys have made, right? Riding in the Waymo, for those who have done it, is an extraordinary experience. It's not to say that you have solved all of these complex tasks, but you've solved a lot of them. What are some of the biggest AI or data problems that you still feel like you're facing today?
The short answer is going to be, taking it to, the next order of magnitude of scale, multiple orders of magnitude of scale, and with that come, additional improvements that we need to make it, a great service, right? But just to level set and make, in terms of where we are today, we are driving in all kinds of conditions. We're driving 24/7 in San Francisco, in Phoenix, a little bit. Those are the most mature markets, but also in LA and in Austin, and all of the complexity that you see. Go drive around the city, right? All kinds of weather conditions, whether it's fog or storms or dust storms or rainstorms down here. Like all of that, all of those are conditions that we do operate in, right? So then you think about what makes it a great customer experience, right? Like what does it take if you grow by next orders of magnitude? There's a lot of improvements that we want to make so that it becomes a better service for you to get from point A to point B, right? Like we ask for feedback from our riders. A lot of feedback we get has to do with the quality of your pickup and drop off locations, right? So we're learning from users. Like we want to make it a magical, seamless, delightful experience from the time you kind of start the app on your phone to when you get in the destination. So that's a lot of the work that we're doing right now.
Yeah, pickup and drop off, for what it's worth, is an extraordinarily hard problem, right? Like, do you kind of block a little bit of a driveway if you're in an urban location and then have a sensor that says, oh, actually, I just saw somebody opening a garage door, I need to get out of the way. How far down the street is acceptable to go pull? Or if you're in a parking lot, where in the parking lot do you go? Like, this is an extraordinarily hard problem, but to your point, it's huge for user experience.
That's exactly right, right? And it's just, I think that's a good example of just one thing, one of the many things that we have to build in order for this to be an awesome product, right? Yeah. Not just like a technology demonstrator. And I think you just you hit exactly on a few things that make something that kind of at the face of it might seem fairly straightforward, right? Okay, I know there's a place on the map and I need to pull over. So like, how hard can it be, right? But really, if it's a complicated, a dense urban environment, there's a lot of these factors, right? Is there another vehicle that you're going to be blocking? Is there a garage door that's opening, right? Like, what is the most convenient place for the user to pick up? What is so it really gets into this, the depth and the subtlety of understanding the semantics and the dynamic nature of this driving task, and doing things that are safe, comfortable, and predictable, and lead to a nice, seamless, pleasant, delightful customer experience.
Of course. Okay, so you've mentioned this stat, but 15 million miles. I know the number's probably a little bit bigger than that, but you just released it Tuesday. Yeah, it's growing by the day. 15 million autonomous miles driven. That's incredible. Even more impressive, and you didn't share this stat yet, it results in 3.5 times fewer accidents than human drivers. Is that right?
And I think 3.5x is the reduction in injury, and then it's about 2x reduction in the police reportable kind of lower severity incidents.
This sort of comes to a question of both kind of regulatory and kind of business or ethical judgment. What is the right level that you want to get to? Obviously, you want to constantly get better, but is there a level at which you say, okay, we're good enough, and that's acceptable to regulators?
Yeah, so there's no super simple, short answer.
Right.
I think it starts with that. It starts with those statistics that you just mentioned.
Yeah.
Like, at the end of the day, what you care about is that roads are safer. So then you look at those numbers, where we operate today, and we have strong empirical evidence that our cars are, in those areas, safer than human drivers. So on balance, that means a reduction in collisions and harm. Then, actually, on top of the numbers we've been publishing, this is you're quoting the latest numbers that we shared.
Yeah.
We've been consistently sharing numbers as our service scales up and grows. If you can also bring in an additional lens of how much did you contribute to a collision. And we actually published, I think it was based on about 4 million miles, 3.8 million miles. We published a joint study with Swiss Re, which is, I think, the largest global reinsurer in the world. And the way they look at it is, who contributed to an event. And there we saw like the same theme, but the numbers were very strong, that we feel it was a 76% reduction in police property damage collisions, and it was a 100% reduction in claims around bodily injury. So if you kind of bring in that lens, I think the story becomes even more compelling,
That
right?
is extremely compelling.
Right, but there are some collisions where we'd be, and that's the bulk of the events that we see. We'd be stopped at a red light, and then somebody just plows into you, right?
Sure.
And so, but then, I think we do know it's a new technology, it's a new product, so it is held to a higher standard. So when we think about our safety and our readiness, framing of methodology, we don't stop at just the race, right? We build over the years. One of the huge areas of investment and experience over the years, like what else do you need? So we've done a number of other different things. We've published some of our methodologies. We've shared our readiness framework. We do other things like we actually, not just statistically, but on specific events, we build models of an attentive, very good human driver. Like not distracted human. It's a good question whether such a driver exists, right? But that's kind of what we compare our driver to, right? And it's a model. Like in a particular scenario, we evaluate ourselves versus that model of a human driver, and we hold ourselves to the bar of doing well compared to that very high standard. And then you pursue other validation methodologies. So kind of that's my answer, is that it's the aggregate of all of those methodologies that we look at to decide that yes, the system is ready enough to be deployed and scale.
I'd love for you to talk about what you think maybe today and in the future about market structure, competition, and what kind of role you envision Waymo playing.
So the way we think about Waymo and our company is that we are building a generalizable driver. That's the core of it. And that's at the core of the mission of making transportation safe and accessible, right? And we're talking about ride-hailing today. That's our main, most mature primary application. But we envision a future where the Waymo driver will be deployed in other commercial applications, right? There's deliveries, there's trucking, there's personally owned vehicles. Right? So in all of those, our guiding principle would be to think about the go-to-market strategy in a way that accelerates access to this technology and gets it deployed as broadly. Well, of course, doing it gradually and deliberately and safely, but as quickly and broadly as possible. So with that as our guiding principle, we're going to explore different commercial structures, different partnership structures. For example, in Phoenix today, we have a partnership with Uber and ride-hailing, both in Uber ride-hailing and in Uber Eats. So in Phoenix, we have our own app. You can download the Waymo app and take a ride, and our vehicle will show up and take you where you want to go. That's one way to experience our product. Another one is through the Uber app. We have a partnership where you can get through Uber app matched with our product, the Waymo driver, the Waymo vehicle, and it's the same experience, right? But this is another way for us to accelerate and give more people to experience full autonomy, and it gives us a chance to kind of think about the different go-to-market strategies, right? One is us having more of our own app. The other one is more of a driver as a service for somebody else's network. So we'll it's still early days, but we'll iterate, but all in service of that main principle.
That's amazing. Yeah, that's going to be exciting. Maybe back to the vehicle. What about the hardware stack that you use? You and I have talked a bunch about. You said like, hey, going all the way back to DARPA, it's kind of the same stuff. Right? It's sensor. They've advanced quite considerably, but you still use radars and lidar. Do you think that remains the future path for autonomous driving, lidar specifically?
Yeah. No, I mean the sensors are physically different, right? They have each one cameras, lidars, radar. They have their benefits. Each one brings their own benefits, right? Cameras obviously give you color and they give you very high resolution. Lidars kind of give you a direct 3D measurement of your environment, and they're an active sensor, right? So they kind of bring their own energy. You kind of pitch dark when there's no external light source. You still get see just as well as they do during the day, better in some cases. And then radar is very good at like punching through just physics, different wavelengths, right? So if you build an imaging radar, which we do ourselves, it allows us to give you an additional redundancy layer, and it has benefits. Also an active sensor. It can directly measure, through Doppler velocity of other objects, and it can, it degrades differently and more gracefully in some weather conditions, like very dense fog, or very dense rain. So they all have their benefits. So if our approach has been to use all of them. Right? And that's how you have redundancy, and that's how you get an extra boost in capability of the system. And we are on today deployed in fifth and working to deploy the sixth generation of our sensors. And over those generations, we've improved reliability, we've improved capability and performance, and we've brought down the cost very significantly. Right? So I think the trend for us that will using all three modalities just makes a lot of sense. Again, you might make different trade-offs if you are building a driver assist system versus a fully autonomous vehicle, where that last 0.001% really matters.
Yeah, absolutely. One of the observations that we have from the very early days of this wave of LLMs is that there has been sort of already a massive race of cost reduction, and many would argue that it's sort of a process of commoditization already, even though it's very early days. I would say the observation from autonomous driving over many years now is kind of the opposite thing. There's been a thinning of the field. It's proven to be much harder than expected. Can you just talk about maybe why that's the case?
They always had this property that it's very easy to get started, but it's very insanely difficult to get it, all the way, to full autonomy, so that you can remove the driver. And there's maybe a few factors that contribute to that. One is, compared to the LLMs and kind of AI in the digital world,
video,
right? You have to operate in the physical world. The physical world is messy, it is noisy, and it can be quite humbling, right? There's all kinds of uncertainty and noise that can kind of pull you out of distribution, if you will, right?
Right, sure.
So that's one thing that makes this very difficult. And secondly, it's safety, right?
Sure.
These AI systems, in some domain, this is creativity, and it's great. In our domain, the cost of mistakes or lack of accuracy has very serious consequences, right? So that sets the bar very high, right? And then the last thing is that it is you have to operate in real time, right? You're putting these systems on fast-moving vehicles, and you have to milliseconds matter, right? So you have to make the decisions very quickly. So I think it's the combination of those factors that really together lead to the trend that you've been seeing, is that it's an and, right? You have to be excellent in this and this and this and then, right? It's all of the above. The bar is very high for every component of the system and how you put them together. But there's big advances, and they boost you and they propel the system forward. But there are no silver bullets, right?
Yeah.
And there are no shortcuts if you're talking about full autonomy.
And because of that lack of tolerance for errors, you have a very high bar for safety. You have a very high burden from regulators. It's very costly to go through all those processes, and so it makes sense. And I'm very grateful that you guys have seen it through, despite all the humbling experiences that you had along the way.
It's been a long journey, but it's for me and many people at Waymo, it is super exciting and very rewarding to finally see it become reality. We talk about safety and AI in many contexts, right? It's a big question, right? But here we are in this application of AI in the physical world. We have at this point a pretty robust and increasing body of evidence that we are seeing tangible safety benefits. So that's very exciting.
Yeah, I always say to people, it was a long journey and very costly and expensive along the way. But this is probably the most powerful manifestation of AI that we have available to us in the world today. I mean, you can get in a car without a driver, and it's safer than having a human, and that's just remarkable. What were some of those humbling events along the way?
In those early days, the first couple of years?
Days.
Oh, sorry. I remember there's one route that we did that started, I think it started in Mountain View, then went through Palo Alto, then went through the mountains to Highway 1, then took Highway 1 to San Francisco, and I think went around the city a little bit, and like actually finished through Lombard Street. So like 2009,
That
10
is
people,
that is really complicated.
100 miles from
so
beginning to end, right? So
Those human drivers would fail at that task, I think. So
yeah. So we're doing it one day, and then we're driving. We kind of made it through the Mountain View Palo Alto part. We're driving through the mountains, and it's foggy. It's early morning, and then we're like seeing objects, and objects mean like random stuff on the road in front of us. There's like a bucket and like a shoe, and then there's like at some point we come across like a rusty bicycle. And like, okay, what's going on there? And then we catch eventually, and like the car doesn't handles it okay, maybe not super smoothly, but we didn't get stuck, and we catch up to like this dump truck that has all kinds of stuff on it, and just periodically losing things that present obstacles to the car.
It's like this is like a cartoon continuation of anomalies being thrown at you guys. That's pretty cool. Okay, last question, and I'm going to tee you up to do some recruiting probably, but if you were in the shoes of the audience here and just kind of seeking your first job, I'm going to take something that you said, which is like, I can see your passion and excitement for doing the startup thing, right? And like, kind of longing back for those days is so cool. What advice would you have for these folks in where to go, whether it's type of company, type of role, industry, or anything else?
Waymo?
This is what I'm saying. It's the easiest to just tee you right up.
Yeah. I'd say find a problem. I mean, we're talking about AI today, but I'd say find a problem that matters. Problem that matters to the world, problem that matters to you. Chances are it's going to be a hard one. Many things worth doing have that property, so don't get discouraged by the unknown, by what others might tell you, and start building, and then keep building and don't look back.
A huge congratulations on all the progress you guys have made, and as a very happy customer, thank you for building it, and we really appreciate you being here. So let's hear it for Dmitri.